All right, everyone. I've passed around a stack of old quizzes. So where is that at? Do they go around? They're over there. Okay, so there should be 2 quizzes in there. Okay, so we're going to continue chapter 8. Last time we started with sequences, right? And some notation that we had was this notation. We use a set of braces around this expression. And if we put 1 here and k here, this means that we have a finite sequence, which means the sequence starts and then the sequence stops at some point. Ready? Yes? Okay. If we have an infinite sequence, then we don't put anything here. You could put 1 to infinity, but if you don't put anything, it's understood that it just continues. And so it's a sub 1, a sub 2, dot, dot, dot. Remember, a sequence is really just a function. It's just that we use a different notation for it. And most importantly, it's a function that goes from the integers, the positive integers, into the real numbers. So what it's doing is it's just spitting out, you're plugging in the numbers 1, then 2, then 3, then 4, and it's just spitting out whatever the output is. And so if you look at it graphically, it's a bunch of dots as opposed to a nice smooth curve, right? Okay, some of the things that we spent a lot of time doing, skills, right? This is where I went around the room and I was like, hey, here's a sequence, can you come up with a formula? And that's just something we're going to need to be able to do. We'll get a lot more practice with it, but it'll just be part of a bigger problem. Some of the special sequences that we had, here we go. This is just a few of them. Y'all remember what this sequence generates? The even numbers starting with 2. This would create the odds starting with 1. This would create a alternating sequence. This would start where? With negative, and then this would be alternating starting with positive, right? We also talked a little bit about factorial, and that's where I'm gonna pick up today. I know we didn't leave off here, but there's a few things about factorial that I want to make sure we understand. And then we're going to do a little bit more in 8.1 and maybe move into 8.2. There's still quite a bit of stuff we can talk about in here. So in terms of this factorial, the factorial has some really nice little properties that we want to be completely aware of and be able to utilize when we need it. So like if you write down, let's say n plus 3, and you put that in parentheses and you say factorial. Just want you to realize that this is the same as n plus 3 times n plus what? 2 times n plus 1 times n. So remember, the whole idea is like whatever's in here, factorial means that you're going to start with that number, and then you're going to multiply it times 1 less than that, and then multiply that times 1 less than that, and then multiply that times 1 less than that, and then keep going, right? So if I keep going, what would be the one after n? N minus 1, then n minus 2, and where do you stop? When you get to 1. So times dot, 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 get to 1, we stop. Right, that's what that is? Right? Yes, yeah.
Till you get to 1?
You always get to 1. Yeah, so like when we did like 4 factorial as an example, this just means 4 times 3 times 2 times 1, and that's where you stop.
Okay.
Right? Yeah. So if we say n plus 3 factorial, what we mean is n plus 3 times n plus 2, and you just go all the way down to 1. But here's what I want you to see. From here all the way down is n factorial, right? That's n factorial. Agreed? So this is n factorial right here. So I could rewrite this as n plus 3 times n plus 2 times n plus 1 times n factorial, right? I could. It means the same thing. This n factorial just means this from here down. So it's almost like you're peeling off the first 3 pieces and then going n factorial the rest of the way down. Let me show you how we could use this, okay? Because you might be like, well, why would I need to do that? So let's say we're given a problem and we're asked to simplify 7 factorial over 5 factorial. All right? So instead of doing 7 times 6 times 5 times 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1, since the 7 is bigger than the 5, I could write the top as 7 times 6 times 5 factorial, right? times 5 factorial. Now I could write 5 times 4 times 3 times 2 times 1, but I stopped at 5 factorial because I'm dividing that by 5 factorial. And now the 5 factorials cancel, right? And all you're left with 7 times 6, which is 42. Make sense? Okay, with that same sort of concept in your mind, take a look at this expression. What if we had n plus 2 factorial over n minus 1 factorial? So which of those is bigger, n plus 2 or n minus 1? N plus 2. So what I want to do is try and start peeling off factors, just like this. This n plus 3, it's like you're peeling off factors out the front until you get to n factorial, right? But what do I want to go to? I want to peel until I get to where on the top? N minus 1, right? So I'm going to say this is n plus 2, right? Times n plus 1 times n times then your n minus 1 factorial. So just keep in mind that this little expression right there represents everything from there on, right? And then we're going to divide that by n minus 1 factorial. And so these cancel. And all you're left with is n plus 2 times n plus 1 times n. And then you could expand that out. You can multiply that, but I'm just going to leave it like that. Okay? So we will be playing with things like this where we simplify. Yes?
What's the n at the top? Like where you
What's the what?
n plus 1, you have n.
N? Okay, so you take 1 away from this, right? So subtract 1 from that and you get n.
Which is 0.
No.
0.
Maybe it's plus 0, but you know.
Yeah, n plus 0, if you could look at it like that. N plus 0, which is just n. All right? Okay, so the most common one we're going to see, all right? The most common one we're going to see is this. N plus 1 factorial over n factorial. We're going to see that a lot. And what is that equal to? Just n plus 1. That's just n plus 1. Because it's n plus 1, you peel off the first factor, then n factorial the rest of the way down, and then n factorial, they cancel, you're left with n plus 1. All right? We'll see that a lot, and it's just going to be just something we just do in our heads, all right? How about this one? This, just to see some slightly different notation. What if we have n factorial over 2n factorial? Can we do anything there to make things cancel out? So do you see that on the bottom, the 2n is in parentheses, then factorial, right? Let's see, can we, the top is just n times n minus 1 times n minus 2, all the way down till you get to 1, right? Now on the bottom, what's the bottom? We have to do the same principle, right? So where do I start? What's my first factor? 2n, right? And then 2n minus 1, right? The whole thing, 2n minus 1, and then 2n minus 2, 2n minus 3, and I do that all the way till I get down to 1, right? Does anything cancel?
We can factor out the 2 n's.
The factor out the 2 n's, what?
All three of the terms.
No, these are, yeah, we can't pull a 2n out of each of these. So there's a couple of things that do simplify, but I mean, just in general, it's not like things go away, right? Like you're never going to get up here to cancel with a bunch of stuff down here. Do y'all see the difference? Now, I do see 1n can cancel, right? Like that n. And then there's also this one right here. You could pull out a 2, right? If you pull a 2 out of this, it'll cancel with this one. And will I have another one? Yeah, when I get to 2n minus 4, I can pull out a 2, and I'll have an n minus 2. Huh? So I'm just trying, the main thing for this is that you understand what this is, okay? 2n factorial is 2n times 2n minus 1 times 2n minus 2. All right, so that 2 inside the parentheses is important. I'll just leave that alone. How about this? 2n factorial over 2n, that quantity factorial. So this is a better illustration of the difference between the two. The top one is just 2 times n times n minus 1 times n minus 2 all the way down to 1, right? The 2 is just sitting out in front of everything. On the bottom one, the 2n is inside each factor. So this is 2n times 2n minus 1 times 2n minus 2 down to 1.
So what is putting the factorial symbol on the outside of the quantity here? I missed that.
What is the difference? Well, that's what I'm trying to illustrate here, the difference between these two. This 2 right here is almost, it's just like, a 2 sitting out in front of that expression. So you write down n factorial, which is that, right? And then you multiply times 2. With it being in parentheses, it's part of the factorial. So you're going to take 1 away from this, then 2 away from that, then 3 away from that, then 4. Got it? Okay. All right, with that all said, let's move on. So what I did not talk about last time, what we need to kind of really start, this is kind of the new stuff today, is to talk about the limit of a sequence. Okay, the limit of a sequence. So given a sub n, given an infinite sequence, if we write limit as n goes to infinity of a sub n equals L, so this is the notation we used back in Cal 1, where we're like, okay, we're going to take the limit of something, right? So we want the limit as n goes to infinity of this sequence a sub n. If we say that that's equal to L, then what we mean is that as n gets big, right? As n gets big, the sequence gets closer and closer to L. Now, it may not actually ever get to L, because that was the whole idea in Cal 1 behind limits, is that you let x go to infinity and then your function approached some value. It never had to actually be there or get to that point. Same thing with sequences. If you take the limit of a sequence as n goes to infinity, then if we write this and say it's equal to a number, okay, so I should point out here this is a number, then what we're saying is that the further out in the sequence you go, the closer and closer your numbers get to something, right? Now, do limits always have to exist? Limits do not always have to exist. So we're saying that if we write this, this means that it's going to L. That means that this sequence, this limit actually exists, all right? So if the sequence, or sorry, if the limit exists, we say, what? We say the sequence converges. And write okay, this right here is important. So instead of writing the limit as n goes to infinity of a sub n equals L, instead of writing all that stuff, if we just write a sub n with an arrow pointing to L, what we mean is that that limit exists. It's headed to a number, right? And we say that the sequence converges, all right? Now, if the limit doesn't exist, so if it doesn't exist, what do you think we're going to say? It diverges, all right? Now I'm just going to put otherwise we say the sequence diverges. So in order to say a sequence converges, the limit must exist and go to a number. If that doesn't happen, the sequence diverges. All right? So what if the limit is infinity? It diverges because infinity is not a number. All right? So because of that, any sequence that heads to infinity or negative infinity is a divergent sequence. With me? All right. So let's do a couple of examples. I'm going to give you a sequence. So find the limit if it exists. How about that sequence right there? A sub n equals n. So because we had a long weekend, let's write out this sequence. What are the numbers in this sequence? 1, 2, 3, 4, right? 1, 2, 3, 4, and this thing goes forever, right? It's just all your counting numbers. So if we take the limit of this, we take the limit as n goes to infinity of n itself, right? That's our sequence. It's obvious to everyone that this thing goes to infinity, right? So this thing basically heads to infinity, I'll say. So this diverges. We could say it's, if you want, we can say it's equal to infinity. I mean, it's not, but.
It would be wrong if we said it's equal.
Well, I mean, how technical do we want to be here, right? Well, in math we have a term for that. We say without loss of generality. In other words, like as long as we're like all kind of on the same page, we can say that even though technically infinity is not a number. Okay, here's another example. Same thing. Find the limit of this sequence. A sub n equals 1 over n. Yeah, I mean this goes to 0, right? So the limit as n goes to infinity of 1 over n goes to 0. Right? If you have 1 on top and the bottom's getting huge, that thing's going to start to go to 0. We didn't list it out, but the sequence is 1, 1/2, 1/3, 1/4, so on and so forth. So you can see that the numbers within the sequence are getting smaller and smaller and smaller. They are headed towards 0. Will they ever get there? No. So we can write this. 1 over n, arrow to 0. That means that's the notation that would indicate that this limit exists and it's headed to 0. I think this is obvious. I mean, we've all seen this sort of thing, yeah? Okay, converges, right? All right, so let's try something a little bit harder. Okay, how about this sequence? A sub n equals 1 plus 1 over n to the n. Ooh, okay. So let's see what's happening. This one's not as obvious, right? Maybe we should write out the first few. What would we get if we plugged 1 in there? We get 2, right? What happens if we plug 2 in there? So we get 1/2 plus 1. It's 3/2, but squared. 9/4, right? 3/2 squared. How about if we plug in 3 in there? So we plug 3 in here, 1/3 plus 1, that's 4/3, right? And then we're raising that to the 3rd power.
81.
Right, that would be the next one. What would the next one be? Let's see, we're plugging in 4, right? So it'd be 5/4 to the 4th, and so on, right? That's what's going on. So what is the limit then as n goes to infinity of this expression.
It's getting bigger.
Yes? I'm asking, yeah. So what, you think it's 1? It's not, but no. But what's your rationale behind getting 1?
I like 1 because if you put in a really big number like infinity, you have 1 over infinity, which is like 0, and 1 plus 0 to infinity is 1.
Okay, so this is why I'm doing this example. That's a good, the idea here is that if n is huge, right? If n is huge, and huge is subjective, but 1 over a huge number should be a very tiny number, right? And 1 plus a very tiny number should be really close to 1. But you're raising that to a really huge number, right? So, but, well, here's the thing. This right here, no matter what n you pick, do you all agree that this is a number that is greater than 1? Yes? And then you're raising that to a power that's really big. So if this right here was the number 1, if it was 1, identically 1, 1.000, okay, then 1 to any power is 1. But it's not 1.0 forever. It's 1.00 with some other stuff, right? And if I raise that to a huge power, it's going to get bigger. But at the same time, this is getting closer to 1. So who wins? Does anyone know what this limit is? It's E. It's actually E, the letter E, 2.718. This is actually the definition of E. You could define E to be this limit. Now we have to show it though. Okay, so that's a different task. All right? So in Cal 1, this is what we call an indeterminate form, where you have something like this. The base is approaching 1 and the exponent is approaching infinity. I'm not saying the base is 1. I'm saying the base is approaching 1, and then the exponent is approaching infinity. And anytime you have something like that in Cal 1, if you did L'Hopital's rule, that section, this is an indeterminate form, we have to do something.
Derivative of the numerator.
Yeah, we have to do L'Hopital's rule, okay? But there's a huge problem right now. L'Hopital's rule is assuming we're working with functions. Nice, curved, like smooth functions. These aren't functions. These are dots, right? This is a bunch of dots on a graph. And so to take a derivative, look, I mean, let me just, L'Hopital requires derivatives, yes? But to take a derivative, you have to have some smoothness to your curve. Like if I, if I tell you, excuse me, look at that curve, go to that point, take the derivative, everyone would understand that I'm asking for the slope of the tangent line there, right? But now we're not dealing with this. We're dealing with this. Dot, 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 dot. And if I tell you to go to that dot and take the slope of the tangent line, you don't have a curve, right? You don't have a curve. You can't really do that, can you? So at this point right now, with this sequence, we're leaning towards wanting to use L'Hopital's rule, but we can't because of that situation, right? So we have a theorem, all right? So the theorem's about to help us. All right, so the theorem says this. So right now I'm going to say, question mark, how do we deal with this, right? These other ones, the first two I put up there were obvious limits, right? N and 1 over n. Like it's obvious to see what they're doing. That one, not so much. So here's the theorem. It says if A sub n is a sequence and we define f of n to be a continuous function on the interval 1 to infinity, then the limit as n goes to infinity of a sub n equals the limit as n goes to infinity of f of n. So what is this theorem saying?
If we approximate the series with a function, together with a curve in between, you can use the limit of the function to limit the series.
Yes, there's one word you use there, approximate.
It's not really, because you will not every point.
Exactly. So what this is saying is I'll give you a real quick example of this. let's say we take this example of a sub n equals 1 over n. Now we know the limit of that is 0, right? That sequence converges to 0, yes? Now if we look at the picture of this, we'd start out at 1, it spits out 1. We then go to 2, it spits out a half. And then 3, it spits out a third, and so on and so forth. What this theorem is saying is that, look, if you take a sequence and instead of just plugging in 1, 2, 3, 4, 5, 6, define a function to be that sequence, but on the entire interval from 1 on, with all the stuff in between, then whatever the function does, the sequence does. So we have, if we fill this in, if we do this, but now we look at it as a function of n, using all the real numbers from 1 on, then we're going to fill these in, right, with a smooth curve like this. We will also pick up the same dots, right? Those dots will still be part of our curve. So whatever the blue curve does, the sequence does. Make sense? It's a pretty simple fix, but we have to formalize that. And there will be times on your test when you have to do this, and I need you to notate the fact that you're using the theorem. Okay, because you can't just take, you cannot use L'Hopital's rule on sequences. You can only use them on continuous functions. So you have to, in your notes, say, while you're doing the problem, say, oh, and I'm using the theorem that allows me to do this, right? If you don't do that, then it's technically wrong. Make sense? We'll do examples, and I'll show you how you're going to illustrate that. Okay, so let's get back to that problem that we had. We were looking at a sub n equals 1 plus 1 over n raised to the n. And when we just looked at this limit right away, we got this indeterminate form 1 to the infinity. So the first thing I'm going to do, because I think I'm going to need L'Hopital's rule, is I'm going to define a function to be this same thing, and I'll define it on the interval 1 to infinity. So now this should be a continuous function. Do you agree that it's a continuous function? How do I know that's a continuous function? Is 1 over n a continuous function? Everywhere but 0, right? But we're not looking at 0. We're going from 1 on. So that's continuous. My microphone on? I feel like I'm forgetting something. I know I'm recording. Mic's on. Okay. So this is a continuous function except at 0, but we're not concerned. We add that to 1, that's still continuous. And raising something to the n power is like an exponential function. So if you take a continuous function and raise it to an exponent, we should still have a continuous function. So this is all a very nice, smooth, well-behaved function. So now we can use L'Hopital's rule if we want. But to use L'Hopital's rule, you have to have 0 over 0 or infinity over infinity, right? You can't use it when you have 1 to the infinity. So I'm just going to go through this because I know some of you have seen L'Hopital, some haven't. The way that you do this is we're going to try right now to find the limit as n goes to infinity of 1 plus 1 over n raised to the n. Okay, that's what we're trying to find. So the standard protocol here when you have this form is to make an equation out of this and call this something. Now in my Cal 1 class I usually call this y, but you can call it any letter you want. You want to call it L? We can call it L for the limit. Let's just call it L for the limit. We want to know what that limit is, right? And now what we do is we bring in the natural log on both sides of the equation, or we use the one-to-one property of natural log. So I'm going to do natural log of the left side equals, now the property of the natural log is that it can pass through the limit. So I can leave the limit here and put the natural log in front. And why is it that we bring the natural log in on both sides?
That you can put then.
Yeah, we can use property of logs that says if you have natural log of something to a power, the power can come out in front. Okay, that's the whole reason we did it at this point. So now we bring, I just covered this in my Cal 1 class last class. So this kind of seems like I'm repeating this, but I'm not. So limit n goes to infinity. So the n came out, then I still have natural log of 1 plus 1 over n. Okay, so now take a quick look at this. What happens as n goes to infinity here? As n goes to infinity, well, this piece goes to infinity, right? So this piece right here is getting really big times, now, let's see, 1 over something really big is headed to 0. 1 plus 0 is headed towards 1, right? And natural log of 1 is 0. So this piece here is, well, the whole thing is headed to 0, right? It's not 0. It's headed towards 0 because it's headed towards a natural log of 1, and natural log of 1 is 0. Yes?
I apologize. How do we get from, like, what's the purpose of the natural log on this one?
This n came out in front.
Right.
And you can only do that with a natural log.
Bring the unknown exponent.
Property is this. This is just the property of logs from college algebra. So that n can pop out. Whatever the power is on the argument can come out. Okay, so we have now something that's getting really big times something that's getting really small, right? This is still an indeterminate form. We still don't know the answer. Do not look at this as being infinity times 0 and anything times 0 is 0. That's not the way you look at this. These are limits. That's approaching infinity. That's approaching 0. There's like a tug of war, right? One wants to be big, one wants to be small. So now, the way we handle that, let's see. Any of my Cal 1 students gonna make me feel good about life right now or no? Okay, what are we gonna do? Yeah, what's the algebra trick? You drop one down. Good job, you win. We drop one of them down. So we have two factors, and we're going to choose one of them to drop down to the numerator. Now, we usually pick the easier of the two. So I'm going to leave the natural log 1 plus 1 over n here. And then what we're doing is we're rewriting n in the denominator as 1 over n, which is the same expression as, these are exactly the same expressions, because you would just reciprocate that n back up, right? But there's something you gain from this. If we take the limit now, the top is still going to natural log of 1, so the top is still going to 0, right? But now where's the bottom going? 1 over n goes to 0, and now you have an expression that looks like 0 over 0. And now you can use L'Hopital's rule. Okay? So, natural log of L equals, now whenever we use L'Hopital's rule, we either put like an L or an H over the equal sign. I always put an L. So limit as n goes to infinity. Now I can take derivative of the top and bottom separately, right? That's what L'Hopital's rule says. Did you get caught up on L'Hopital?
I watched the video.
Okay, so it helped. So if any, was that enough to feel like you kind of know what's going on a little bit?
It was good.
Okay. So if anyone else is like, what, L'Hopital? You went and found my Cal 1 L'Hopital rule video and watched it? Okay. So there's stuff out there. Okay, I can't reteach L'Hopital in here right now. So I'm going to take the derivative of the top here. The derivative of the top is going to be, well, derivative of natural log of something is 1 over 1 plus 1 over n, right? That's just basically 1 over the argument, times chain rule, derivative of the inside, derivative of 1 is 0, plus derivative of 1 over n would be negative 1 over n squared. And I'm getting that by rewriting that as n to the negative 1, and then just doing power rule. Negative 1 comes out, subtract 1, then rewriting it as a fraction. Now, that's derivative of the top. What's the derivative of the bottom? Same as the derivative of that, right? So negative 1 over n squared. And these cancel. Wonderful. And now we can take the limit. As n goes to infinity, this becomes what? That goes to 0. 1 plus 0 is approaching 1. 1 over 1 is 1. So the answer is 1. I thought I said it was E. I did say it was E because we're not done, right? What we're saying now is that the natural log of L equals 1, right? So we wanted to know what L was, right? So how do we get rid of, we're going to undo the natural log now. To undo the natural log, we come in with E on both sides. So my last step here, I'll put it right here. My last step here is to take e on both sides. So e raised to the natural log of L equals e raised to the 1. These cancel off. We get L is equal to e. So the limit is e. I'm just applying e to both sides of the equation to undo the natural log. All right, yes? So this limit, a little more involved, yes? So just be aware that all these things from Cal 1, where you had all these indeterminate forms, are now on the table again. But the thing is, we have to first state, okay, look, we've got a sequence, right? I'm going to need L'Hopital, so I'm going to convert it to a function. Once I convert it to a function, then I can do all the stuff I did in Cal 1, and whatever that answer is the answer to my sequence limit. Yes?
So that notation right there, the let f then equal
Uh-huh.
the notation from 1 to 20, that's the notation.
That would be fine. If you just wrote that down, I would know that you understand that you have to look at these as functions, a continuous function. Okay? Fun stuff, yes? All right. How about this one? New sequence. Let's figure out what the limit of this is. Square root of 3n plus 1 over 5n plus 3. All right, so I want to know what the limit of this sequence is. So what is the limit as n goes to infinity of this? So what's going on inside this root? The numerator is becoming infinite, right? The denominator is becoming infinite, so you have infinity over infinity. But it's under a root, right? So can you use L'Hopital here?
Unless you convert them to square root of top times over square root of the bottom.
I don't even need L'Hopital in the series.
You don't what?
You can't use L'Hopital in the series, so we can't use L'Hopital.
What do you mean, in the series?
I'm saying convert it to a
It's still a
function.
series, so we can't use
That's
L'Hopital.
the sequence.
Still a sequence, right?
Yeah, this is still a sequence right now. So we can't use any L'Hopital until we explicitly state we're going to look at this as a continuous function first. But right now we have infinity over infinity square root, right? So that's like what happens. We don't know. But infinity over infinity is actually a good thing to see because we do have L'Hopital. We just have to state it real quick. So we're going to say let f of n equal that function, right? On this closed interval. And now we've pretty much said, hey, we're looking at the continuous function that includes all my dots, right? Did I mess something up?
3, not a 1. 5
Oh, yeah. Okay, I just wrote that down. Okay, right there. Okay, so now we can do everything that we did with continuous functions. Yes?
Can I say that I think I see something?
Yeah, sure.
Are we going to do the same thing and using the natural log of raising it and then pulling the 1/2 out and then being able to use those?
I would not use the natural log here because the indeterminate form we had before, this one, that indeterminate form, that's 1 to the infinity is what indicates you should use the natural log. The other indeterminate forms that would cause you to use natural log, or if you have something that looks like this, 0 to the 0, that's an indeterminate form. Infinity to the 0 is also an indeterminate form. So if you ever see any of these, you want to bring in the natural log. Here we have infinity over infinity. So it's almost like it's ready for L'Hopital, right? Derivative top and bottom. The problem is the square root. But there's something good about that. If I take the limit as n goes to infinity of this, there's a property of limits that allows me to push the limit inside the root. So you are allowed to do this. This is a limit property back from Cal 1. Why do you have to have Cal 1 before you take Cal 2? I guess for things like this, right? Okay, so now, see, on the inside here, we can do L'Hopital. And so what I'm going to do is I'm going to indicate that I'm using L'Hopital. Limit n goes to infinity. And square root. And now we do derivative top and bottom, which is just going to be 3 over 5. And that's the answer. Pardon? Why did I take the limit? Don't know why I took that. I'm sorry. That was bad. Limit n goes to infinity. Sorry about that. That's what I meant to write. Thank you. The reason why I took that is because it's Monday. That's why.
Just out of curiosity,
Yes.
this whole deal is like f of n equals, right?
Yep. Everything that I'm doing here is based upon this right here. All right. So our answer is just square root of 3/5. So the limit of that sequence, right? The limit of that sequence is square root of 3/5. All right, let's do another one. How about 5n factorial over 5n plus 2 factorial? All right, what about this? As n goes to infinity, what does 5n factorial do as n gets bigger? So if I'm taking the limit, as n goes to infinity, of 5n factorial over 5n plus 2 factorial. So what happens if that number gets huge and I do times 5 and I do the factorial? Is that getting big, small? What is it doing? It's going to get big, right? I mean, plug the number 100 in here, right? So that'd be 500 factorial. That's pretty big. That's 500 times 499 times 498. Now plug the number 1,000 in there. Now a million, now a billion, now a trillion. That thing's getting huge, right? Yes? And so is the bottom. So we have infinity over infinity, right? So you might be thinking, okay, L'Hopital? No. Yes? Yeah, like do what we did a minute ago, right? That's what we're going to do, but I want to make sure everyone's clear. We can't use L'Hopital here. Like you don't have that option now. Why not? Because factorials cannot be converted over to continuous functions. A factorial is only defined on the integers. So you can have like 0 factorial, 1 factorial, 2 factorial, 3 factorial, but you can't have 1/2 factorial. Well, you can, but it's outside this class. That's another class. Okay? For us, and I said this last class, factorials are only defined on integers. So if you tried to convert this and go, oh, I'm going to call it a function on a real number line, right, from 1 to infinity, you can't. Okay? You can't. So since L'Hopital is not at play here, we have to use some other technique, and then I guess it's what we did just a little while ago, right? Rewrite it. Which of these is bigger, the top or the bottom? Here the bottom is bigger, right? So I'm going to leave the 5n factorial alone on top, and I'm going to rewrite the bottom as what? 5n plus 2, 5n plus 1. What's the next one? 5n, and then factorial, right? And now those factorials cancel. The 5n factorial and the 5n factorial cancel. And so what we're left with here is limit as n goes to infinity of 1 over 5n plus 2 times 5n plus 1. And is that obvious? That goes to 0. Bottom gets huge, numerator stays at 1, that's going to go to 0. I'd like to do 2 more, and then we'll move on. Okay, next one. How about this one? Negative 1 to the n. Does that sequence converge or diverge?
Up, down, up, down, up, down.
Yeah, if we look at this, at 1 it's negative 1, and at 2 it's 1, and then negative 1, then 1, and then negative 1, then 1, and then negative 1, then 1. Is that going to converge to a number? No. It's just jumping back and forth. So this one, what? Diverges. And that would be just by inspection. Okay, just by looking and say, oh, look, that thing alternates up and down, diverges. Okay. How about this one? Negative 1 over n to the n. So what would this be written as? If we plug in 1, what do we get? Negative 1. If we plug in 2, what do we get?
Negative 1. No, 1, excuse me.
If we plug in 2, we get negative 1 over 2, but then squared. So we get 1/4. And then what about the third one? We plug in 3, we get negative 1/3, right, raised to the third. Negative 1 over 27, right? So on and so forth. What does it look like that one is doing? It looks like it's converging to 0, doesn't it? But how would we show that? I mean, you can't use L'Hopital's rule with this, right? Or anything like that. You don't have like infinity over infinity. It's just, so what do we do? So we have another little theorem, okay? We have another little theorem that's going to help us get around these right here. So I'm going to leave that as a question mark. Maybe 0, right? I don't know. So here's a theorem. If the absolute value of a sequence converges to 0, then the sequence without the absolute value converges to 0. So theorems are basically truths, okay? And so we just accept these and then we use them. So go back to this one right here. Go back to that one. If we look at a sub n equals, I'm going to rewrite it, negative 1, let me see if you agree with this. Negative 1 over n to the n, is that not the same as negative 1 to the n times 1 over n to the n? Is that the same? That's the same thing, algebraically. All I did was I rewrote the inside of this as negative 1 times 1 over n, right? Rewrite that as that, and then I apply the n power to both of these, and that gets me to here. Okay, so that's a sub n, right? This theorem says, look at the absolute value of this. So what is the absolute value of this sequence? So if I take the absolute value of negative 1 to the n times 1 over n to the n, what part of this no longer matters? The first part. This doesn't matter, because no matter what that is, it's going to be 1 or negative 1, right? When you take the absolute value of it, it's going to be 1, right? And on top of that, this over this to this power is always a positive number, because n is either going to be 1, 2, 3. We're not plugging negatives in here. So would you agree that the absolute value of a sub n is just 1 over n raised to the n? Right? Now, what does this go to? Well, that in here goes to 0, doesn't it? So this thing's getting smaller, and this thing is doing what? Raising it to bigger powers. Is that an indeterminate form? It is not. We just had a problem a second ago where it was this, right? And that was an indeterminate form. Because the base is like, hey, I'm trying to be 1, and the exponent's like, but you're not 1, you're a little bigger, and I'm going to try and make you even bigger, right? Here, the base is headed towards 0 and the exponent is headed towards infinity. This is not an indeterminate form because as this number gets smaller, what happens when you take a small number and raise it to a bigger power? It gets smaller, right? Like if you take 1/2 and square it, it becomes 1/4. If you take 1/10 and square it, it becomes 1/100th, right? So this is trying to get small. This just helps it get smaller faster. So this is headed towards 0, right? So we are looking at this sequence. We were kind of like, I don't know. The theorem said, look at its absolute value. If the absolute value goes to 0, then what can you say about the original sequence? It goes to 0. So the answer to this is that it converges to 0. Does that make sense? Use the absolute value, then whatever it does, the original one does, right? Did I say that right? I just said if you're having trouble with the sequence, look at its absolute value. Whatever the absolute value does, this one does. Say it again. Does this theorem say that when you're looking at a sequence, you look at its absolute value, whatever the absolute value does, the sequence does? That's not what this says. This says that if you're looking at a sequence and you look at the absolute value of it, if the absolute value goes to 0, then the original sequence goes to 0. I'll show you an example of a problem where this is used incorrectly. So look at this sequence we did just a second ago. We said that diverged, right? Okay, so then I'll have a student come over here and try and use this theorem. They say, okay, I'm going to take the absolute value of that sequence. The absolute value of that's that, right? But no matter what comes out of that, the absolute value of that's going to be 1, right? So this is 1. So then they'll say, oh, okay, since the absolute value converges to 1, that means that converges to 1. Wrong. If the absolute value converges to 0, then you can say that the sequence goes to 0. But if the absolute value converges to something else, this theorem, throw it in the trash. It's not going to help. Make sense? Okay, so this is basically useless right here. All right, did that one. Okay, a sequence that's going to come up quite a bit is this one. So, an important sequence. And here it is. A sub n equals r to the n, where r is a real number. What we're going to do is we're going to look at this, and we're going to see if we can come up with a general answer for this. If somebody just tells me what R is, can I tell you if it converges or diverges? So let's take a look at a couple of obvious ones. What if R was 0? This would converge. Do you all agree? Right? 0, right? If R is 0, then this sequence becomes 0 to the n, which is just the sequence 0, 0, 0, 0 forever, right? And that converges to 0, right? What's another obvious one that should, if R is 1, okay, so if R is 1, then we have a sub n equals 1 to the n, but that's just 1, 1, 1 forever, right? So that would converge. So if R is 0, or if R is 1, we have convergence, don't we? Okay. What if R is something between 0 and 1? What if R is, let's say, just bigger than 0 and less than 1? Can we tell what's going to happen? We're going to have a sub n equals r to the n. So what happens here? It gets smaller, right? Because again, let's, as an example, if you pick like 1/2, right? then your sequence would be 1/2, then 1/4, then 1, maybe I should write. So as a specific example, if r is 1/2, right, then your sequence is going to look like this. 1/2 to the first power, right? 1/2 squared. 1/2 cubed. 1/2 to the fourth, right? And what's happening each time you go out is that's getting smaller and smaller and smaller. And that should work for every number between 0 and 1. Do you all follow that? Okay, so far, what can we say? I mean, out of all this together, where are we? If r is anywhere between 0 and between 1, I mean like up to 1 and including 1, what do we have? Convergence. Now, I'm not even asking what it converges to, okay? What have we not looked at? Bigger than 1? Let's go with some numbers bigger than 1. So what's a number bigger than 1? 2? So let's see. What would happen if we had 2 in here? If r is 2, then we have 2 to the end, don't we? And what's that going to look like? 2, then 4, then 8, then 16, then, right? 2 to the first, 2 squared, 2 cubed, 2 to the fourth, right? That's just going to blow up, right? This thing's just going to become infinite. And that would work for any number that's bigger than 1. You do 1.5, it's going to start getting bigger as you raise it to bigger powers. Do you all agree? So it looks like right now, if r is greater than 1, just greater, then we have divergence. What have we not considered? Negatives. Negatives. Don't want to do that? We have to, sorry. So let's consider some negatives. So let's consider an easy negative first. How about if r is -1? If r is -1, we would have that this is -1 to the n. And what did we say about that already? It diverged, right? Did we say that diverged? So we get divergence. Okay. What about if r is -2? Think about what that would be. It would look like this. -2, what would be the next term? 4, +4 then, -8, then 16. It's pretty much this one, right? But with the added thing that it's going positive, negative, but it's still blowing up, isn't it? It's blowing up, but switching between positive and negative. So is that headed to one thing? No, it's diverging. And you can make that argument for any number that's, what, to the left of 1? -1? Right? So it looks like from that, oh sorry, this is divergence. What we could say is if r is, what, less than or equal to -1? Right? Because at -1 it diverges. And what we're saying is anything to the left of that, it's going to diverge also. We're going to do a final summary here at the end, but I'm just kind of going through all the options. What's the one set of numbers I have not done yet? So -1 to 0. Everything between -1 and 0. So maybe something like -1/2? Okay, so if r is equal to -1/2, then we have -1/2 to the n. And what would that do? Let's see what that looks like. -1/2, 1/4, -1/8, 1/16, ... right? Where are those headed? Smaller and smaller, headed to 0. In fact, you could use the theorem we just used, or just got a second ago, to take the absolute value of that. If you take the absolute value of that, then you're looking at only the positives, and we already said that that goes to 0.